All right, so as you all requested, I'm going to try to talk a little bit faster in this video. Also, this topic just isn't going to take me as long to explain, so hopefully this video is quite a bit shorter than the last one. Let me go ahead and show you the slides here. So we're still in Unit 1, Atomic Structure and Properties, but now we're on to Topic 2, which is about the mass spectroscopy of elements. Okay, so let's go ahead and dive on in. As I said in the first video, each time we go over a new topic, I'm going to show you this from the AP course exam and description. So the learning objective for today's topic is to be able to explain the quantitative relationship between the mass spectrum of an element and the masses of the element's isotopes. Okay, so what we're going to be doing today is we're going to be talking about atomic structure, isotopes, and I'm going to make a brief mention about ions. I'll explain what AMUs are, atomic mass units, and then we're going to get into some of the details of mass spectroscopy. Okay? Then in the next video, the problem solving or example problem video, I'm actually going to show you how to use data from mass spectroscopy to calculate the approximate average atomic mass for an element. Okay, and you're going to be able to do that with graphical or numerical data. Okay, so a lot of this video should actually be review from your chemistry class last year. This right here is referred to as the Rutherford model of an atom. We are only going to be using this model temporarily to understand the structure of atoms, and this is going to soon change. But what this model shows us is that atoms are essentially made of three things. They are made of three things. Protons and neutrons in the center of each atom, and then electrons not in the center of each atom. We're definitely going to learn a lot more about where electrons are and their properties at a later date. The protons and neutrons together in the center of the atom are in what is called the nucleus of the atom. Note that this is not some sort of special enclosure or anything like that. The protons and the neutrons together are referred to as the nucleus. Okay? If an atom had a single proton, that proton would also be the nucleus. All right? So those subatomic particles, the proton, neutron, and electron, have some properties that I think you probably ought to write down. Protons are positively charged, electrons are negatively charged, and neutrons are neutral. One interesting thing to note here is that the positive charge of a proton is exactly equal but opposite to the negative charge of an electron. Okay? So these perfectly balance each other out. If you have one proton and one electron, the overall charge would be 0. Okay? Their masses in kilograms are listed here. Interesting little piece of information. The proton is actually slightly smaller than the neutron. Okay, it's not a very significant difference, but it is slightly smaller. You can see that given that this is measured in kilograms, right? 1 kilogram is fairly substantial. It's a pretty decent amount of weight. These subatomic particles, kind of like how we talked about in the last video, are so small that if you were to measure them in kilograms, they are 10 to the minus 17. That's the order of magnitude that we're looking at for a proton and a neutron. And then electrons are even smaller. Okay, so this Rutherford model, these things are not drawn to scale. Okay, the electrons are the same size here. That is not the case. Not in the way that we think about things typically, like size, nor in their mass. So electrons have an even smaller mass, 14 powers of 10 smaller than protons and neutrons. So this is one way to think of the mass of these subatomic particles. Another way to think of the mass of subatomic particles is in the unit AMU, which stands for Atomic Mass Unit. Basically, what this means is that protons and neutrons essentially have a mass of 1 in this unit system, and electrons are so small compared to those protons and neutrons that they essentially have no mass at all. Okay, and that isn't exactly true. That's why this says approximately 0. But for most calculation purposes, it is the mass of an electron is negligible. And then once again, I have their location listed here. We're going to talk a lot more about the specific location or locations of electrons at a later time when we talk about electron configuration. Okay, so you guys have a periodic table, and you've seen periodic tables before, so like once again, this is going to be some serious review content. Each entry on the periodic table has a number of things inside of it. The number at the top is usually the atomic number. The large 1 or 2 letter symbol is the element symbol. There may be an element name. And then this number here at the bottom usually has some decimal places here. This is referred to as the atomic mass, or sometimes the atomic weight. Okay, so really this should say mass. I should change this picture to say atomic mass, but I just haven't gotten around to that. Now, I do want to take a moment to go and look at your all's periodic table. This is the AP Chemistry periodic table. You will notice that there is one thing missing from all of these entries, and that is the element name. Okay, so I don't know if this is something that I have to look into. I don't know if on the AP exam they are ever going to give you the name of an element without giving you the element symbol. I can't imagine that they are expecting you to memorize all 118 element names and symbols. I suppose that's possible. I will look into that. Okay, but there is a reason why, for example, if you had me last year, we did sort of memorize all the way up until element number 36. Those elements towards the top tend to be the more commonly used elements in chemistry problems, I mean, and generally just in the world around us. And so that's why we did that. So anyways, back to this. So some notes about this entry on the periodic table. The atomic number is equal to the number of protons that you're going to find in an atom of that element, okay? And this is extremely important. This is always true, okay? The number of protons in an atom determines what element that atom is. The number of protons is like the identity of the element, okay? And there aren't very many easy ways to change the number of protons in an atom. So take note of that, okay? The atomic number is equal to the number of protons. I'm going to talk about electrons here in just a second. In a neutral atom, okay, meaning neutrally charged, sometimes you'll see this term used. In a neutral atom of X, Y, or Z, the number of protons is equal to the number of, that should say electrons. Let's go ahead and fix that real quick, okay? So in a neutral atom, the number of protons is equal to the number of electrons. And that is because, if we go back here, the protons and electrons balance each other out in terms of their charge, right? So if the atom is neutrally charged, then its number of protons is equal to its number of electrons, in which case you can use the atomic number to tell you both of those pieces of information. If an atom is not neutrally charged, then it is called an ion, okay? And we're going to get into this later, not today, but at a later date when we start talking about like ionic bonding, for example. But just so you know, if you see this term referred to, ions are atoms with a non-zero charge, meaning there's either more protons than electrons or more electrons than protons. Okay? All right, this term here, the atomic weight, or really that should say the atomic mass, on the periodic table, these numbers are actually the average atomic mass, and we're going to learn a little bit more about that later. Generally speaking, the mass of any given atom is equal to the sum of its protons and neutrons. Okay, so for example, an atom of hydrogen may have 1 proton and 0 neutrons, and so its mass would be 1. However, as we're about to see, there can be some atoms of hydrogen that don't have a mass of 1. They have a mass of 2, for example, or 3. And in that case, they would have 1 proton, right? Because it has to have 1 proton if it's hydrogen. And so then that would mean that it either has 1 or 2 neutrons, right, to get those masses of 2 or 3. And like I said before, electrons do not substantially contribute to the mass of an atom, okay? All right, so I was just mentioning how some atoms of hydrogen have different masses, and that has to do with this phenomenon here, the presence of isotopes. Okay, not all atoms of an element are the same. Most elements, and when I say most, I mean virtually all elements have several different versions of themselves called isotopes. Some elements only have two different isotopes, two different versions of themselves, while some have very, very many, like double digits number of isotopes. Isotopes of an element have the same number of protons. Okay, so if we were to talk about the isotopes of carbon, for example, all of those isotopes would have 6 protons, but they have a varying number of neutrons. So that is the difference between different isotopes of an element. It is the number of neutrons. Okay? Generally speaking, isotopes of an element tend to behave the same way since their identity, right, or their number of protons is the same, but they do differ in the fact that they have a different mass, okay, and that actually can matter in some situations. Just to give you guys an example here, I've got a diagram of the isotopes of hydrogen here. Hydrogen does have 3 isotopes. They're referred to colloquially as protium, deuterium, and tritium. Also, their more systematic names, or like official names, are hydrogen 1, hydrogen 2, and hydrogen 3. Okay, this right here, protium, is the most common form of hydrogen by a long shot. Okay, so we're talking like 99+% of hydrogen that exists in the universe is protium. Okay, and it looks like this. It's got 1 proton and 1 electron, 0 neutrons. Okay, so the overall mass of this atom would be 1. Okay, because remember that electron doesn't really contribute to the mass very much. The second most common version of hydrogen, which is still not very common, less than 1%, is deuterium, which is just this atom with 1 neutron added to it. And then the third type, and the vastly least common version of hydrogen, is tritium, okay, hydrogen 3. And it has 2 neutrons. Okay, so once again, it's the protons and the neutrons in the nucleus that determine the mass. Okay, I have a little funny story that I want to tell you about the isotopes of hydrogen. So I was mentioning before on this slide that generally isotopes of the same element tend to behave the same way. Okay, but they do differ in the fact that they have different masses. That actually matters a lot in the case of hydrogen specifically, okay? Because think about it. This atom here weighs literally half as much as this one, okay? And this atom right here weighs 1/3 of this one, right? So for really small elements like hydrogen, helium, etc., the different isotopes actually can have pretty different properties due to this significant difference in mass. Now, if I was to talk about the isotopes of iron, for example, iron is a fairly big element, atomic number 26. The mass difference there isn't super big compared to the overall size of the atom. But in this case, the mass difference is huge, right? This is literally twice the mass of this one. So, water, which is H2O, has 2 hydrogen atoms in it. Most water in the universe, well, I don't want to say that, but probably a majority of the water that's in the universe is made up of hydrogens that are this type of hydrogen, right? So that's fine, right? It's got some 2 protium atoms there, no big deal. Some water, and this water is referred to as heavy water, is made up of hydrogen that is actually of this form, deuterium. Okay, and in fact, heavy water has the chemical formula of D2O. It's kind of like an unofficial formula because D is not actually the chemical symbol for hydrogen, but that's kind of what it's referred to, D2O. That version of water has like twice the weight in its hydrogens, right? Because the hydrogens are twice as big or twice as massive. So it's actually pretty interesting. If you drink heavy water, pure heavy water, you can actually get sick to the point of dying because your body is not used to the way that heavy water works. Your body is used to the way that light water works. So this is not something that I think is going to be like specifically assessed on the AP exam. I just thought it was something interesting that I wanted to tell you about. Okay, so moving forward. Isotopes, their names are written in what is called hyphen notation. It looks like this: the name of the element, and then a dash or a hyphen, and then the mass of that specific isotope. So for example, hydrogen-1 or helium-4. As you can see down here, we had hydrogen-1, hydrogen-2, and hydrogen-3. So that number there is the mass number of the isotope. And then isotope symbols, or nuclear symbols, can also give you similar information. They look like this. The top number here, it's sort of to the top left of the symbol, is the mass number, once again. And the number to the bottom left is the atomic number. Sometimes this atomic number will be omitted. Okay, so sometimes you'll see a nuclear symbol that just doesn't have this number 2 here. And the reason for that is if you know what element it is, then you know what the atomic number is. So it's not really necessary information. Sometimes you'll see it there, sometimes you won't. So don't be thrown off by seeing a nuclear symbol that doesn't have the atomic number here. If you have that mass number, that's really what you need to be able to work with that isotope. Okay? All right. So this is getting to the actual learning objective for the topic. So we need to learn a little bit about mass spectroscopy. And I don't have any written notes here, but some of the things that I say you might want to write down. Okay? We don't have to be like experts at mass spectroscopy. We don't have to know every little detail of how a device like this works. But we do need to understand the general gist of what's going on here because it may be asked on the AP exam. Okay, so I'm just going to give you the nuts and bolts of what's going on here, and as always, if we have questions about this, we can talk about it when I see you next in class. Okay, so this blue stream of material here is an element, okay, that's being sent through. It's one element, a pure element, that's being sent through a vaporizer and some ion accelerating stuff. This is all really not that important, okay? All you need to know is that this blue beam is all one element, okay? It may contain, and based on what we see here, it does contain different isotopes of that element, okay? This device, the purpose of this device is to separate the element stream or beam into its different isotopes or its different versions, and then to measure how much of each version there is using this detector plate. Okay? So, this right here is the important part. The magnetic field. Okay? As the beam of the ions or of the element goes through this magnetic field, the different isotopes of the element are going to interact with that magnetic field in a different way based on their mass. Okay? So here's how it works. The least massive or the smallest isotopes are going to be affected by the magnetic field more so than the most massive or biggest isotopes. Think of it this way, okay? If you were on a playground and you had a jump rope, you were holding one end of it and your friend was holding another, and you were like spinning around, right? Let's say your friend is the same size as you, right? So you kind of have equal pull with each other. Okay, now let's say you find the biggest kid you know, right? And they take the other end of the jump rope from you, right? They are going to, you are not going to be able to have as much pull on them as if you found someone who is much, much smaller than you, right? If you find somebody that's really, really like much, much smaller than you, you could really tug them around, right? You can impact their path of motion more so than you could impact the path of motion of the bigger person, right? That is kind of what the concept is here, okay? I'm kind of skipping over some of the physics that goes on here, but that is basically how this works. The least massive isotopes are going to be pulled in the direction of the magnetic field more than the more massive ions will. So essentially what happens here is as the beam goes through, the elements or the isotopes will separate into separate beams according to their mass. Okay, with the least massive ions getting pulled more and the most massive ions getting pulled less. Okay? When you perform mass spectroscopy, the whole point of doing that is to get some data about the element that you are analyzing. Let's say that we were looking at neon, for example. Okay? There are 3 isotopes of neon. First of all, you could figure that out by running this experiment. Make sure that you have a sample of neon, run it through a mass spectrometer, and you would find 3 peaks on this detector graph. Okay, the data that you would receive is you would get 3 peaks. That would tell you that you have 1, 2, 3 different isotopes of that element. Okay, and the way that the detector is calibrated and the way that the data gets spit out to you is that you would actually know what the mass number is for those different isotopes. Okay, so even if you didn't know that this was neon, okay, you could see that this was mass number 20, mass number 21, mass number 22. If I go and take a look at my periodic table and I look for elements that have mass numbers or atomic masses of around 20, the only element that I see is neon. Okay, so this is in real life how scientists can identify an element. If you have a sample and you think it's a pure sample, you can send it through, and based on the mass numbers you get, you can tell what you've got. Okay, so that is the data that you might see. Now, we're going to work with data like this and data like this in the problem-solving version of this video to learn how to calculate like the average atomic mass for neon. One last thing that I'll say before I finish things up here is that using this graph, you can come up with, or using this data, I should say, you can come up with a bar graph, okay? What we're doing here basically is like some fancy math. Imagine that this straight line here continued all the way across, okay? If you then measured the amount of area in each peak, okay, so you'd have a lot of area here, not very much here, and then maybe a little bit more there, you can come up with these numbers, okay, this relative number of atoms. So it takes a little bit of fancy math to turn this raw data into these specific numbers, okay? But if you can do that, then you really have some useful information. You can use this data to calculate the average atomic mass of an element, okay? And I'm going to pick back up with that in the next video when we actually do some problem solving with data like this, okay? All right, thanks for watching, and I'll see you in the next video.